Oh, beginning programming thing. What class is this? Did we already start a? Oh, we were just talking about it.
We were just talking.
Okay. So let me actually go ahead and create a project for this. Actually, before we do that, let's kind of review here. Okay, so we're talking about n-ary trees, where it's we lose that structure that we had for binary trees, where everything to the left is less than or equal to, everything to the right is greater than, but we kind of get the ability to store multiple things under a single parent, single top level. And we kind of drew out a little, so I said kind of a good example for us in here, and this is so a good example for programming students is how n-ary trees are used for, sometimes they're called syntax trees. In this case, which is an implementation of an n-ary tree, is we might have this idea of we want to represent a statement. Okay, so languages like Java are statement-based languages. They're essentially collections of statements, and we're not going to look at a complex language. We'll look at just kind of simple statements like little mathy type stuff. But essentially, you might have a tree that represents a single statement. All right. And so think back to when we first started talking about Boolean expressions last semester. And we said any expression that boils down to a single value of true or false. And we used some examples. And I said it's very important that you focus on resolving an expression before you come up with what its answer is, right? Because you might have something that looks very complex with all sorts of ands and ors and less thans and greater thans, all this stuff. But in the end, it's still just a single value of true or false, right? All right, so with that in mind, a syntax tree would kind of explode out all the details that go into a single statement, or in that example, a single expression. All right, so in our example here, we tried to represent this guy, okay, which by our normal standards, we would say is not an overly complex expression, correct? It's not an overly complex expression, but this seems like it's fairly complex, doesn't it? Okay, so we're going to say this entire thing is a statement. That's why at the very top we have statement. Okay, and remember, Java is a collection of statements, so we would really have a top level thing called program. So when you think about your entire program, it would just one line of code, one statement you have in your program like this would turn into something like this. And how many of those one lines of code do you have in your project? Several hundred would be pretty common for us in our projects that we're doing in here. All right, so certainly 100 and 150 lines of code might be. So this times 150 is what represents your project. Make sense? So we'd have a top level called program, and off that top level we'd have statement, 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 all the different statements, and each of those statements would then branch off into the details of that statement. Similarly, if you get into like object-oriented programming or modular type programming, you might have program, then inside of there, so for Java we might have program, then method, 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 field, right? Constructor, something like that. And then each method would then explode into parameters and then the statements that are inside the method, that kind of stuff. So it really becomes an organizational tool. So when we think about n-ary trees, we really want to think about something as being relatively flexible for organizing data. And the reason why we might want to organize data is so we can come back and use the data at a later point in time. Make sense? Okay. So we have this idea of a statement for our little world here. So this whole thing is a statement, so we started off here. We decided this is, if we had to describe what kind of animal this is, we'd say, oh, well, we're setting a variable, right? We have a variable A, and we're setting it equal to this crap over here, okay? So that means this is probably like a var def statement, a variable definition statement. We can call it whatever we want, but that kind of is just descriptive, right? Okay, so this is a variable definition statement, and the generic syntax for a variable definition statement might be a variable, followed by an equal sign, followed by some expression, followed by a semicolon. Okay, that's our expected syntax. Now, as I'm going through this again, what I want you to be looking forward to, or dreading, one of the two, is this idea of what we would actually use this structure for. I'm going to ask you at the end of this, why? It's not just to torture you. Okay? So why do we have this? All right, so start thinking about that in that context. All right, so we take our Var Def statement and we decide what should that guy look like. He should look like this. A variable expression followed by an equal sign, followed by an expression, followed by a semicolon. Okay? Then, from that, we have what? Well, a variable expression is just A. Our expression is actually a math expression. Okay? Well, what kind of math expression do we have? Well, we actually have a somewhat complex math expression, correct? You know, if we make this a little bit more generic, this is left minus right, where in this case, left is actually parenthesis left times right minus right. Make sense? See how I'm making it a little bit more generic so we can kind of see the pattern? So this entire thing is a math expression. But this first piece of it is also a math expression. So really we have a math expression minus a math expression. So from this, something we'll talk about next semester, we're not going to get into it in here, but we have a grammar. Well, actually, how many of you are taking 470 next semester? Okay. I don't know, programming language theory is what I call it.
Yeah, just programming languages.
Programming languages. Yeah, class is a nightmare. So good. I love that class. It makes the stuff we've been doing in here look like you're playing with like Play-Doh. So this will give you a little taste of it, except we're not going to go into anywhere near the detail we'll go into in there. But we'd have something called a grammar. And a grammar for a math expression might be, a math expression is, so math EXPR would be a number or a left followed by an op followed by a right, or an open parenthesis followed by a left followed by an op followed by a right. Actually, let's think about this. Write this a little more generically. This would be a math expression followed by an op followed by a math expression. All right, and then we have a third form, which is just parenthesis math expression, like that. So these are the forms that our math expression can take in our little world here. It can just be a number, so like 5 would be considered a math expression. Okay? It could be a, I suppose we could actually throw a var expression in there as well. That could potentially be a math expression as long as it held a number. So you can see how this can get pretty complex pretty quick. Okay, so, but in any case, just to kind of go with what we have here, this isn't a language class. We're focusing more on the tree structure side of things. Just it happens to be that syntax trees are a good example for this. All right, but this is kind of what we're getting at with this. All right, so over here on the right-hand side of the equal, we have our expression. And this guy happens to be a math expression. How did we know it was a math expression? Well, it fit this grammar. So let's just say that's the case. Fit that grammar. So left-hand side of a math expression is an expression. In this case, we might call it a math expression. The right-hand side is a math expression with an operator in the middle. Okay? So this expression was a math expression. The operator was a minus. This guy was a var expression, which just boiled down to C, which ultimately boils down to the value that C holds, which is defined someplace else. Not important for us in here. All right. But the math expression in this particular case happened to be a parenthesis expression, this version of the grammar. Okay. It's called a production, this production of the grammar. All right, so it's a math expression, which happens to be a parenthesis expression, which starts with a parenthesis, followed by a math expression, followed by an op, followed by a math expression, followed by a closed parenthesis, in this particular case. Why? Because a parenthesis expression, I think I said last time we were running out of room, so really this should say parent expression, open parenthesis, math expression, close parenthesis, should look like this last production here. Then we'd explode it out to this line, which would then give us what's on the left, which is a var expression, followed by the operator, followed by what's on the right, which both boil down to that. Okay, so this is a really complex way of describing that one line. Why? What's the purpose of this? Outside of torture. We haven't even written it yet. This is just the problem we're going to solve.
Does the computer to solve it down to like the simplest terms, pretty much, or break it down?
Okay. Why? Why does the computer have to do that?
Because it's just a bunch of ones and zeros at the end.
What would we use this for? So when in what kind of setting would we see something like this? If you go to Arby's and you're checking out the menu, would you see this at Arby's?
No.
If you saw this at Arby's, actually that would be kind of funny, wouldn't it? Like value meal 1 and value meal 2 just has like a weird like integral integration. That would actually be pretty funny if I ran a fast food joint. I might do that. Just have crazy math formulas, or you actually give your the cost in like some sort of weird algorithm that ultimately produces like $2.99 or something, but you actually have to solve for X or something like that. And it deals with the current temperature outside, so it's actually a variable expression.
You get buy one get one at the day's next or the previous day's temperature at McDonald's.
Yeah. Yeah, if you're a Bucks fan, I think I haven't actually been to a game this year, which is weird because I used to have season tickets to the Bucks, so I used to go to all the games. I have a couple of whatever it's called, the crazy fan one where you attended every game, and we got to go out in the court and shoot during halftime and stuff. But I didn't go to one game this year. That's weird actually for me. But in any case, I assume they probably still do the thing with McDonald's where you can take your ticket in and get like they do like 2 snack wraps or something like that. You get, if the Bucks win, you get something free with your ticket at McDonald's.
By X amount of points.
Huh?
By X amount of points.
Oh no, it was if the Bucks win and scored 100, at least 100, I think was when I used to go. The people at McDonald's weren't watching the game. You just swing through McDonald's and hand you your ticket and go, yeah, go Bucks. Get your free burger and leave. Christian worldview. Don't do that, Christian worldview.
Does George Webb's actually check? Because they still do the burger thing with the Brewers. Granted, I don't know if the Brewers are going to score.
I would think as you got up to, yeah. Obviously George Webb isn't, a high-end place, but I think in terms of as you go up the pecking order in terms of the cost of the food, you have to think they'd start paying more attention to giving away free stuff, right? Okay, so how do we get onto that? Whether we'd see this on the RB menu. Got it. Okay, that's not the setting we would see this in. So when would we see something like this in our world? So on a computer, when would we see something like this? Would you see it in your Word document when you're writing your paper for your philosophy class?
No.
No, when would we see this?
When we're programming.
We're programming for us, right? We see stuff like this all the time when we look at our code. All right, so what things are involved in our when we program from a computer's perspective? We write a text document, right? And in this text document, we have a bunch of lines of code. What's happening behind the scene? When we go into Eclipse and we hit this little play button up here, what's actually happening? It's getting compiled, right? It's getting compiled. Whether it's compiled or interpreted, in either of those cases, it's having to go from what we typed into something that can run on the computer. Okay? Now, ultimately, as you point out, it's going to end up being zeros and ones broken down into instructions and things like that. But before we can even get to that level, we have to kind of organize stuff we have to keep rearranging things into some sort of order so that finally we can say the assembly language version of this is this. The assembly language version of this is this. We have to get it down to this little micro pieces. Because remember, a low-level language like assembly language has a one-to-one relationship with the CPU. Well, what does that mean? Well, that means that we have to break our high-level language down to pretty granular pieces before we can finally start converting those granular pieces into assembly code. So what I'm really getting at there is that even this wouldn't cut it. This is the 5,000 foot view. We need the 2 centimeter view for that guy. Okay, so this is just taking our 100,000 foot view and breaking it into a 5,000 foot view, kind of seeing the details. Okay, we're not even under the microscope. We're using binoculars, right, to look at it. So as the compiler or the interpreter, however we want to look at it, as it's going to go through and look at this line of code, it has to break this, I like to think of it as exploding out this line of code into a syntax tree so that it can traverse this tree for various purposes with an ultimate goal of turning it into a low-level language. That's the ultimate goal. If it's an interpreter, we're actually not turning it into a low-level language. We're turning it into something else. Turning it into something else for a low-level language, something that will run on that computer, run on some interpreter. So given that, what we want to do in here is we want to kind of go through a somewhat similar type of experience. And we want to be able to take something that looks like this and convert it into its equivalent JSON. Okay, we've talked about JSON in here a little bit, right? Okay, anybody not familiar with what JSON is? Idiot. All right. I'm just teasing you. Most of the time when I ask if we've covered something in a class, I'm actually asking whether we've covered something in the class. I teach a lot of classes, so we're going to be doing this in JSON. JSON is just a data representation language. And the real reason I'm targeting JSON here as opposed to just our own little made-up language is just so you're kind of learning about an industry standard. Okay, so as an example, let's just kind of take this line. So perhaps, whoa, that kind of wasn't what I was expecting. Still not what I was expecting. That's what I'm expecting. This is okay, you got this. All right, so in any case, this is our mathematical expression. Now, maybe the JSON equivalent to this might be something like opening, let me actually, just so it'll look a little cleaner rather than putting it all on one line. Yeah. Voice is shot. So it might, all JSON objects start off with an opening, closing, curly brace like that. And this guy might be of type what do we call it? A var def expression. Okay, and within this, we're going to have a, I don't know what we would call this, well, let's look at our syntax tree to see what we called it. So we called this guy a var expression. Var expression is going to be A. So that's what's on the left of this. So var expressions are a var expression or var def expression is a var expression followed by an equal sign followed by a math expression in our world. simple. We have a language of math in our little programming language here. We're not doing anything bigger than that for us. All right, so var expression is what's on the left. Equal sign we're not even going to represent, and we'll talk about that here in a second. Then we have our math expression. And the math expression in this case is going to be what? Well, a math expression is actually another JSON object. Okay, so the value associated with math expression is an object. So a math expression has a left and a right and an operator. All right? So we're going to have left is, in this case, a math expression. Followed by an op, which is, in this case, what was my, let's do this, do this. Okay, so this is my language. So my op here is minus. Then my right is actually a var expression, which, just so we don't go too deep with this, since we're not actually resolving stuff, we're not going to write a functional language. We're representing what a functional language might work with. So I'm not going to take this down anymore. A var expression is just going to be represented as the variable name. All right, so right in this case is going to be that guy. Okay, just C. So now we're going to go back and deal with our left, because left is actually an object in and of itself. It's a math expression. Okay, so in this case, it's a math expression that has a left, a right, and an op. So left is A. Op is times, and right is B. Does that make sense? So this would be the JSON representation of this. So this entire thing is a var def expression. Okay, so we just gave it a type. If we were only dealing with a language of var def expressions, we wouldn't even need to give it a type, but this is fine. We'll give it a type. So think of these as this is a dictionary. So this is variable value pairs. So this is a collection of variable value pairs. So everything between this opening curly brace and this closing curly brace is a collection of comma delimited, comma there, so on and so forth, comma delimited variable value pairs. So the first variable is the variable name type. Its value is the string var def expression. Second variable is a variable name var expression. Its value is just A. It's the name of our variable. Third variable is a variable named math expression. Okay, so this is the math expression, which is representing everything that's over here. Okay, because what's on the right-hand side of our var def expression in our little mini language here is, isn't it funny how it already looks pretty complex? It's like we gotta keep calling it mini language, trivial language. Oh, 470 is gonna just make you quit. Oh, it's gonna be awesome. Love that class. Okay, so are you?
Yeah.
Don't you like a challenge?
This class just sounds like nothing but fun.
It's my favorite class. And we use a brand new language. We use a language in there called Scheme, which is a functional language. It's a superset of a language called Lisp. So, yeah. So best thing about Scheme that you're gonna hate: no loops. You do everything recursively.
Is Lisp hard to understand?
Can we just use
That was a joke.
Have you ever tried to read Russian?
That was a joke.
Oh, the list part. I get it. That's why we use scheme. It's a little bit less of a,
Can we just use your new app so we don't have recursion?
well, wouldn't most of you say that recursion is one of your weaknesses? It's hard to think recursively, right? Yeah. When you come out of 470, you won't have a problem. Okay. In fact, a pretty common thing is when you come out of 470, you have trouble transitioning back to thinking iteratively, then being able to choose what's the right tool for this job. One's not better or worse than the other. There's a right time and place for both. You'll get good at recursion in 470. Oh my God, I'm so excited. I've actually had students break down crying in class. In that class. It's so good. Just love that. All right. So, in any case, we have our math expression. So, third variable is a variable named math expression whose value is actually another JSON object. Okay? JSON is a format. Okay, it's not something that we're inventing here. We're utilizing the format. Similar to HTML and XML, it's a format for representing data. That's why I call it a data representation language. Okay, so the value associated with this variable happens to be another JSON object. Okay, so it starts with an opening curly brace, ends with a closing curly brace, just like our top level one here. Okay, so this guy has a variable called left, and left is another JSON object. Okay, it's another JSON object. In our language here, the only JSON objects we have is var def expressions and math expressions. So if it has a type, for us, if it has a type, it's a var def expression. If it doesn't have a type, it's a math expression. For our simple, trivial language that little kitty cats could do.
I'd like to see that.
All right. I have a really smart cat, and then I have a really dumb cat. Okay. So it's our math expression, which is another JSON object that has a variable called left. Left is also another JSON object. Why? Because the left-hand side of this math expression is actually a math expression in and of itself. Okay? So his left is a JSON object whose left is A, whose op is times, whose right is B. So there's a complete JSON object, and that's as simple as it gets for a math expression. 3 variables, 3 values. Left is A, op is times, right is B. Okay? And then we have the op associated with our first math expression, which is the minus. That's this guy right here. And then we have the right associated with our first one, which is our C right here. All right? So our goal, kind of what we're trying to accomplish here, is to read in a string that looks like this. Take in a var def expression and turn it into this as our output. Okay? That's the starting point, ending point. The question is what's in the middle? What's that filter look like? What kind of juicer do we drop this guy into so that this comes out? Make sense? Man, I love those juicers when they spin around really fast, but they're terrible to clean. You know what I mean? Any of you use those centrifugal juicers? You don't know what I'm talking about? Really? You see the old guy on TV, the juice man guy?
Dude, like shoving carrots and
Yeah. You just see, yeah, you see the juice coming out on one side and all like the roughage on the other side. Yeah, there's an old In Living Color skit. Did you ever see that show, In Living Color? There's an old skit that had this guy who was spoofing that old guy from the Juice Man commercials. You know, where the guy's like, I'm 241 years old. It's like, I can still pull a 747 with my teeth. Just the guy's kind of nuts. So he drank some of his juice, and then he decided he could fly.
The juice weasel.
Yeah, the juice weasel. That's it. that's okay. We'll watch it. Talked me into it. Wait until you see me fly, Jordy. You know, this is Jim Carrey. This is where Jim Carrey got started on In Living Color.
Welcome to Juice Mania, the show that takes a look at the wonderful world of juice. This week, the Juice Weasel. And now here's your host, Gordy Langston.
Hi, everybody! Are you as excited as I'm being paid to be? We're ready to! Oh, that's all right, and it's also incredible. Hey, let's bring out today's host, the incredible, most amazing guest we've ever had, Juicy J. Cornish. Come on! Wow, Juicy J, that was an incredible feat of strength.
Thank you, Gordy. I took my whole family on long trips like this.
Well, wow, man, where's your family now, Jay?
They're all dead. I outlived them all.
That's the beauty of the Juice Weasel. Wow, that's incredible.
Come on up. Come on up. You seem like a healthy young man. How old are you?
I'm 21.
21, huh?
Yes, sir.
He's 21, but I'm still standing. I found the secret of eternal life. I looked into God's eyes, and you know what I saw? The Juice Weasel.
Hey, folks, can you tell me what time it is? Time to juice! Juice, juice, juice,
That's how much organic matter you need every day. Now, you can eat it in that form, but sooner or later, you're going to get tired of wiping your butt. Another problem is fruit. How do you get at it? Look, what do I do with it? You need to be a NASA scientist to get inside that thing. Have you ever tried to drink a raw carrot, Gordy? It can't be done.
Wow, I get it. Now that's where the Juice Weasel comes in.
Yes! The Juice Weasel separates the fiber from the juice, saving only the most essential elements. That's the beauty of my design, Gordy. I want you to try something.
Sure, Jay.
A little concoction I made before the show.
Okay. Ooh, that tastes like somebody's dirty undershorts.
Not just somebody's, Gordy. They're mine. But see, the undershorts are gone. All that's left is the life-giving juice.
That's incredible.
See, people like to eat the bad stuff and throw away the good stuff. Look at the celery, Gordy.
Look at it.
Where does it come from?
The dirt, Jay?
No, the soil. You see, the soil is the most important thing on Earth. That is Mother Earth, giving us our gifts. All life emanates from the soil. It emanates, Gordy. See, so what I do is knock out the middleman. You got all the minerals you need right here. That's going to be beautiful, Gordy.
Sure is, right, guys?
Hell with them. You know, another question people ask me, Gordy, is, Jay, what am I going to do about my finances? Groceries are too expensive. Yeah, bet that good, you son of a... You know, I could just go off on them. I'd love to juice them sometime, you know? Just put their hand in there. You know? But the Juice Weasel can take yesterday's leftovers and turn them into today's smoothie.
Sounds pretty good to me. But what do you mean, Jay?
Well, here's a little bag of garbage I took off my neighbor's lawn. Most people throw eggshells away. Bad mistake. Oh, look at this, Gordy. We got lucky.
Hey, wait
We got lucky. See, you know, when I see people throwing stuff like this away, it just makes me want to scream.
Oh, come on now. Insects?
Don't ever question me, Gordy. I know a lot more about nutrition than you do. All right, that's just about ready. Okay. Now watch this, Gordy.
Okay, Jay.
Juice, 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 juice,
Notice anything different, Gordy?
No, what, Jay?
I'm invisible!
Oh, right. Yeah, that's incredible. I thought you were talking about something else.
Who are you talking to, Gordy? I'm over here!
Wow, that's incredible, isn't it, audience?
animals are flying by themselves. You think that's great, Gordy? Wait till you see me fly.
Wait a minute. Wait a minute. That's not in the script.
I
Jay?
can fly, Gordy. I swear I can. I can
Leon,
fly.
stop tape. Wait,
I
what?
can fly.
Jay. Oh my God, he jumped out the window. Stop tape. Oh, he jumped. Jay, are you all right?
It's getting dark. It's strangely peaceful.
Oh my God. Jay, do we need a priest?
No, Gordy. Just give me the juice. Could you pour some of that on my joints, Gordy? I feel much better now, Gordy. That proves one thing to me. There's a time to laugh,
A time to cry.
a time to live, and a time to choose!
Did we get talking about that? Oh, this centrifuge thing. Yeah, that's right. What's the guy in the middle that takes this and turns it into this? Okay, that's where this comes in. Okay, so now taking that explanation, actually, I'm going to copy this slide here. When we think about what a Var Def statement looks like, so we would look at this and say, okay, that's a variable being defined, right? Okay. Now, there's aspects of this that are extraneous that we don't need to store. For instance, the equal sign. That's just part of the syntax, correct? It's part of the syntax. The minus sign. Part of the syntax. We need to know about the operator, so we're going to store it somewhere. What about the parentheses? The parentheses is what dictates that guy being a certain type of math expression. But once you know it's that type of math expression, do you need to worry about the parentheses? We don't need to store them anywhere. Notice in our JSON here, we're not representing those anywhere. Having that opening parenthesis just dictated that we were jumping into this this situation. This situation. Our second math expression. Okay? So, if we were going to modify this tree a little bit, because we ultimately want to turn this string into this tree, onto a tree, which then allows us to produce this JSON. That's what we're trying to accomplish here. Okay? We'll definitely start off with a statement, although maybe in our language we've decided that everything in our language is a Var Def statement. So we can probably remove statement from this. This is our only kind of statement right here. Okay? A Var Def statement. Now, a Var Def statement has what in it? The left-hand side is going to be a variable expression. Then it's going to be a expression. What's on the right? So we actually called this a math expression over here, right? But we don't need to remember the equal sign or the semicolon. It's part of the important syntax, especially the semicolon really is part of the syntax when you have to know when one statement's over and you're going to the next statement. But in our little language here, we're dealing with one-liners. One-liners. So the semicolon is actually unimportant for us. All right? So we have our Var Def statement, which has two elements in it. A var expression and an expression. Or in our case, it's a math expression, which we actually already wrote. So we can just bring this guy up. Just do this. Okay, so this is as far as we go over here. Now we have our math expression. A math expression is what? It's a math expression followed by an op, followed by a math expression. So this is a math expression. followed by an op, followed by a math expression. Our op is the multiplication sign. Let me get rid of most of this stuff here just to give me some space. The second math expression is actually just our C. We've decided we're even representing numbers in our language. Just we have variable names and we have operators, just to keep it as simple as possible. Okay, so our math expression on the right is just C. Math expression on the left is actually a math expression. How did we know that? Well, because it started with an opening parenthesis. And what's a math expression? Well, a math expression is a math expression, followed by an op, followed by a math expression. We can spread these guys out. Go that route for right now. Okay. Math expression followed by an op, followed by a math expression. Well, we know on the right-hand side of this math expression, we have a B. We know the op is a times. And we know on the left, it's an A. Is that a tree representation of that expression? With us leaving out extraneous things that we didn't need? Question is then, how would we build this guy from this guy? This is just a string, and just like any other string, we walk them from beginning to end. So I start walking my string. Now I happen to know, excuse me, we know, or we can assume in our program that whoever inputs something, they've given you legal input. So they've given you something that follows the rules of a math expression. Okay? You have a question, or are you just stretching? All right. So we can assume that this whole thing is going to be a Var Def statement. Okay, that's what this guy is. All right. So we know right off the bat that we're looking for whatever's to the left of the equal sign. So we're going to start walking this guy, ignoring white space. So even if there's 5 spaces before this guy, ignore, 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 ignore. We finally hit something that's not white space. We're not going to hit an equal sign yet because I've told you can assume it's legal. So we're going to build up what's on the left-hand side. We know this guy will be a var expression, okay, because we're dealing with a Var Def statement. Okay? Now, for our simple language here, we can even probably omit the var expression thing, because we didn't reference them as var expressions here. So we'll just store it like this. So we'll read in our first symbol, that guy. So what we did is we started building up symbols. So read in, so maybe we have a function called read symbol. So ignore white space, ignore white space, ignore white space, ignore white space, ignore white space. Found something, concatenated onto our symbol. Ignore white space. So our symbol right now is just the string A. Then we hit the equal sign, which tells us we are done reading in our symbol. Add it to our tree. Okay? So we're going to add this to our syntax tree. We're going to have to come up with a way of labeling it, but we'll get there in a second. All right, so now we read in the equal sign. The equal sign is really meaningless in terms of our syntax tree. It just told us when we were done reading in the first symbol. Make sense? So I added it to my tree. Then we move past that, read in the next symbol. All right, so ignore white space. So if I had white space in here, we're going to ignore, 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 ignore. As soon as I start reading in a symbol, I'm going to look at it. In this particular case, we read in a parenthesis. And we know that parentheses dictate that this guy's a math expression. that we were expecting a math expression anyway. So notice here that we said, I want a math expression. That's what I need here is a math expression. Well, what's a math expression? A math expression looks like this. Do I want to do it that way? I'm going to leave it the other way. This is good. So we're expecting a variable and a math expression. That's what we're expecting up here. So right off the bat, we can go ahead and add a math expression to our var def statement. Okay, just the generic description math expression. So each of these guys is a symbol. Okay, and in our language, we have several symbols. We have a var def statement symbol, which is just our top level. So that's kind of our root node, if you will. We have things that, well, then we have math expression. We have op. And we have things that look like ops. Okay? When it's none of those, it's a variable. So those are the players, if you will, the symbols that make up our little math language here. So we've read in the A. Now we know that the next thing we're going to be expecting is a math expression. Okay, so we're going to be reading in a math expression. So we go ahead and add that, then we say read math expression. Ignore, 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 ignore. We hit an opening parenthesis. As soon as we hit that opening parenthesis, we know this is a new math expression. So we're going to add that there on the left. New math expression. Okay? Then we're going to process this math expression. Pause that for a second. So we know we're going to be dealing with this right now. But following that, we're going to ignore white space. When we finally read in this symbol, we know that's our op. And then we read in our last math expression, which is just a variable. Okay? Now, by our definition here, math expressions are always just either variables or these parenthesis things. So we really could do that. We really could do that since we know what our operators are. So we're simplifying our tree here. We can get rid of op here, move this guy up here. We can get rid of this guy, move this guy up here. We can get rid of this guy. Keep going around the corner. We can get to this guy here. All right. Now, having said that, when we have a var def statement, we're saying A is equal to something. Well, maybe it could just be another variable. So we're going to say, we don't even need to say math expression there. So now we can bounce this up. Okay, so we knew that when we started parsing through this, we walked through it one character at a time. We knew we found out what was on the left. We knew we were then going to look for the equal sign to tell us when we were done reading in that symbol. Burn past the equal sign, then start reading in what it's going to be equal to. Okay, what it's going to be equal to. It's going to be equal to, we start reading in this very next symbol, and we see it's a parenthesis. Right off the bat, that tells us that we're dealing with a math expression. Make sense? Right off the bat, we know we're dealing with a math expression. Now, because we hit this parenthesis, let me actually change this just for a second. Let me copy that. Let's say we didn't hit a parenthesis. We read in our A, hit the equal sign, so now we know we're reading in whatever's on the right-hand side of the equal thing, whatever we're assigning to A. As soon as we read in A, what did that tell us? If you're looking at this, do we know that A is the end of the road? Or are we not sure yet? We don't have enough information to know that we're done. So we don't know if we're stopping at this point. We don't know if it's, our expression could look like this, couldn't it? We could say A equals A, or, maybe more intelligently, A equals B. That would be legitimate for our var def expressions, correct? Okay, so when we first read in something, we don't necessarily know what it's going to look like, right? But in our example here, we're always going to assume that we're assigning math expressions to our variables. So we know what this right-hand side should look like. Structurally, we know it should be a math expression, which means it's going to be something followed by an operator followed by something. So the very first thing we're going to look for is what that first something is. How do we know we're reading in the first something? Because we haven't hit an operator yet. Okay, so when I go over here, I'm looking for my first something, my left followed by right. I'm ignoring, and now I start reading in something. As soon as I read in that opening parenthesis, I know that my left something is actually kind of a complex something. It's actually another math expression. And what do I do when I'm looking for math expressions? Parse math expressions. So I'm starting to think about the code for this. This whole thing here is parsing a var def statement. In our case, parsing a statement, which is always going to be a var def statement for us. So I'll call, if I'm kind of making a list of things I would do in this guy, I would say, first, call parse statement. After I call parse statement, I'm going to start walking through this, and parse statement is going to find this guy, then find this guy, and then what am I going to do? I know the very next thing I need to do after I found the first parts of the statement is I need to do parse math expression. So I'll call parse math expression, which kind of takes over where I left off. All right, so parse math expression is going to start walking through our string starting right, well, it'll start right here. And parse math expression will ignore, and then as soon as we hit that, we say, oh, this is the beginning of a new math expression. So I'm going to call parse math expression, call parse math expression again to parse this math expression. When is this math expression done? This guy right here. When I hit the closing parenthesis. The opening parenthesis told me everything I needed to know about this guy being a new math expression. The closing parenthesis told me that I'm done with that math expression and now I can continue with my previous one. Okay? So maybe think recursion for a second. Put the current one on hold, this top level one. Put that guy on hold because we need to go and parse his left-hand side, which is a math expression. All right. Then we're going to find the operator. Then we're going to find the right-hand side, which in this case happens to not be a math expression. It's just the end of the road. So parse statement, parse math expression, parse the other math expression. And what does parse math expression do? If we kind of explode each of these out, we're going to say read var, then read equal. Well, actually, why don't we say read var read math expression. How do we read var? We'll do that right. How do we read the var? We'll do that right inside the parse statement. How do we read the math expression? We do that by calling parse math expression. While we're reading math expression, it's an extra mathy expression. So how do we read the math expression? We call parse math expression. While we're parsing math expression, we actually bump into another math expression. Well, what does it mean to parse a math expression? Parse math expression means read left, read op, read right. As we were reading left, we actually determine that guy's actually another math expression. So what did we do? We call parse math expression. So this will be the order of our function calls, method calls. To get the ball rolling, we'll call parse statement. Parse statement starts off by reading our variable all the way up to the equal sign, which tells us we're done, ignoring white space. Then we'll call read math expression. Okay, read math expression will go through and it will, read math expression means to call parse math expression. So this is a method. That's calling that method. This guy's a method, parse statement. Okay, so this method does these two things. It reads a variable, it reads a math expression. What does it mean to read a math expression? It means calling another method, parse math expression. What does this guy do? He reads left. Then he notices in this case that reading left actually is going to require us to parse another math expression.
So would we need another read math expression?
We do. We have it right here.
That's parse.
Yeah, parse math. When I read left, I understand what you're saying. To kind of put it in this.
Yeah.
I understand what you're saying. So you want me to do that. So when I say I read left, as part of reading left, I recognize that I was actually reading a math expression. Therefore, I had to call my method parse math expression. It's fair enough. All right, so when I was reading left, I determined this guy was actually a math expression. Because he could have been anything, right? He could have, well, not anything. He could have been just a variable. And I would have just been done. It could have been A plus B, and I read in the A and said, good. It's just a variable. Now I know I'm going to ignore white space and wait for an op. Because the next thing that's coming is read op. Good.
This high-level overview, how are we ever going to get to read op or read write if it's parse math and read math are being called?
I kind of meant, I mark these as these are the actual methods. So anything with an M before it is a method. Anything, the other stuff is the steps that you need to take inside that method. Okay, so parse statement, the steps inside of that method is the first thing you need to logically do is read your string until you get to the first, until you read in the variable. Then you know you're there when you hit the equal sign. Okay, then you're going to read in a math expression because you know that what's going to come on the right-hand side of our variable. We've said that over here in our little language, everything's always a math expression over here. That's what's allowed to be on the right-hand side. So that's why we read the var, then we read the math expression. Those are the two logical steps we need to accomplish inside of this method. Okay? So we'll read the var first, then we'll read our math expression. While we were trying to read our math expression, we determined, well, how do we read a math expression? We call parse math expression. So this is another method. So when we called parse math expression's job is to read the left and to read the right. Okay, that's what its job is. Well, read the left, read the op, read the right. Okay, so this guy's job is to read the left, then read the op, and then read the right. So at the high level, that's what parse math expression is supposed to do. In our case here, when we started reading the left, we were just walking through it. This is all still logic inside of parse math expression. We bumped into an opening parenthesis. That opening parenthesis then told us, oh, wait a minute, we just started reading a math expression. We bumped into an opening parenthesis that lets us know this guy's actually a math expression. How do we read math expressions? We call parse math expression.
So then we read left, read op, read right.
Yep. So what's parse math expression? Parse math expression is read left, read op, read right. And it just so happens in this particular case, we're good. Read left, read op, read right. We didn't have to go in any additional levels. Then we finished reading in that math expression. How did we know? We hit the end of the expression because the next thing we read in was the closing parenthesis. We have two ways of ending things in our code right now. One is a closing parenthesis. The other one is our semicolon. Semicolon tells us we're at the end of the line, end of the statement. We're done reading crap. But when we intermittently, not intermittently, when we, what word am I looking for? Prematurely, maybe? When we prematurely hit this closing parenthesis, we knew that, oh, wait a minute. I just finished parsing this particular math expression. Okay? Therefore, I read the left, which meant read math expression, so I called parse math expression. This guy read in the left, he read in the op, he read in the right, and as he was reading in the right, he read in the, if we had spaces here, he would have ignored, read in the B. The next character he read in was a closing parenthesis, which says, oh, you're done with this math expression. So return, end. Okay? Then we bounce back out here where we left off. Now the next thing we're expecting to do is read in an op. Then we're expecting to read in a write. Make sense? All right, so now we have to represent this programmatically. Keep in mind, we haven't even created trees from this yet. Okay, we haven't even created trees from this yet. So what we want to do, go into our code here. Let's create a new project. CSC300 Spring 2015 syntax tree. Create our class driver. All right, and then I'm going to go ahead and give us another class. And we're going to call this guy, we'll call this guy Parser. This is the dude that's going to walk our string. So we parse strings. Ultimately, we'll be converting that string into its equivalent syntax tree, and then walking that syntax tree to generate our JSON. Okay? And the answer to the question that should have been asked right then is, why put it into a tree instead of just converting it right to JSON? And the answer is that we might want to do other things with it other than just convert it to JSON. So if we organize it in a tree fashion, we now have a launching pad to do anything we want with it. Okay? Plus, we're learning about n-ary trees, both sides of that coin. So what's our parser going to do? Our parser is going to have a string called, let's just call this the statement. It'll have a constructor, public parser string statement has a parameter, and we'll say this dot the statement equals the statement. All right, and then we're also going to have to keep track of a pause. And we'll start pause off at 0. Pause is going to keep track of where we currently are in our string as we're walking through it. Okay, this is often called the program counter in normal compilers. I'm going to make these guys private. Okay, these guys are private. Now we're going to have a couple of functions. We're going to have a function called, well, for right now, we'll make it void. It'll be called parse. Okay, I'm just going to leave it like that for right now. And then we're going to have a couple of private functions. So we're going to have private, void. We're going to make them all void for right now until we determine how we're going to use these. So void parse. And then we're going to have private, void, what did I call it? Parse statement. Parse statement. Yep. So parse statement, which needs to be and then we're going to have a private void parse math expression. Okay, parse statement should read a var name and then read a math expression. Okay, parse math expression should read a, well, let's say read left, read op, read right. Okay, that's what parse math expression should do. Parse should do this. We'll call parse statement. We want our parse statement right now to print each time it reads something like red var name equals A. And then reading math expression, something like that. Okay, so this is what it should display. Parse math expression should display something like reading left, red op equals, you know, in this particular case, what was it? Well, actually, the first one we'll bump into is a multiplication. And then reading right. And then whenever you read in a variable, you'll print it out. So red var name blah, red var name blah, something like that. So give us some sort, and you can deviate from this exact syntax if you want, but basically give us some sort of string-based output as to proving that you're walking through your string in a parse type way, reading in the different components that we're eventually going to put into the tree. Does that make sense? So then out here in driver, we're going to create a parser, P is equal to new parser, and we're going to pass this guy a sample string like that. So I threw some white space in there. That way you are guaranteed to have to deal with ignoring white space. All right. And then you'll say p dot parse. So this is what your main should look like. And then you need to write parse to call our things in the correct order. So parse should start walking through this. This should work for multiple things. I should be able to also then create a parse p2.
What's the semicolon for, though?
That tells you you're at the end of the statement. Yeah. You could probably avoid it if you wanted to by just reading you got to the end of the string, but reading in a semicolon is, I want to make it so if you read in this or you read in a semicolon, you know you're done. That way you can just, you don't have to look for white space after that. So I'm just going to give you a easier expression over here. So that might be the second one it should work on. A equals B minus C. I should be able to give it anything that follows our rules here, and it should parse it. Make sense? All right, so I'll put this up on Angel. I'll put the code up. So for Thursday, you won't have to change main at all. This is done. What you will have to do is you'll have to go in here. You won't have to change this. You won't have to change this. You'll have to write parse statement and parse math expression. and make sure that as you're walking through, you're updating. Pause. Pause keeps track of where am I in the statement string. That way, as you're passing, you're calling things parse statement to parse math expression. It knows where to pick up, where to keep going from. Make sense? All right, should be a simple assignment.
Is that sarcasm?
Nah, actually, this one's not bad. You'll spend quite a bit of time on it, but it's really not that bad. In the end, solving this problem is, you could probably do it in 10 or 12, 15 lines of code. Something like that, probably. All right, I will see everybody on Thursday. I'll go ahead and put this up now.
I took a look at it.